We're starting by looking at the first 18 problems on homework 7, which might seem kind of weird to you, but this is all stuff that we did last week. There isn't anything new in these problems, which is why we're going to start with them. And there are some parts that I want to talk about with you, some things that might be kind of confusing, starting with the very first question, which is asking you to select the molecules that contain sphingosine. We talked about sphingosine in section 19.6. It is the backbone for a molecule like sphingomyelin. So right away, you know that sphingomyelin is definitely one of the options. It's giving you another name of molecule, this guy right here that we never talked about, and then it's also giving you 3 drawings over here on the side for molecules A, B, and C. So I want to show you one of the things in your notes. I never actually drew out what sphingosine looked like. I just always represented it like this and then, had the tails attached. So here in molecule A, what I'm drawing a circle around right now, this is the sphingosine backbone. Notice that it's got, actually maybe I want to include the oxygen right there. So there's the sphingosine backbone. Notice that it's got 3 carbons. It's got a nitrogen on the center carbon. That's important. And then it has oxygens on the top and the bottom carbon, and it also has this carbon-carbon double bond. This particular tail is not variable in sphingosine. So all of these atoms are always going to be the same, unlike this particular tail could vary. There's a few different things that this could end up being. Not the case with the stuff that's inside the box. It's always going to be the same. So knowing that that is the sphingosine, then obviously we know that molecule A is also containing sphingosine. And if we look at the structure of molecule B, really what you're looking at is find that center carbon in the backbone right there. And is there a nitrogen on that center carbon? There's not. So molecule B is not going to be does not contain sphingosine. As far as this guy, just type that name into the internet, look up the structure of that molecule, and look for the sphingosine characteristic. And let's take a look at the next problem. Cell membranes are composed of phospholipids. Which of the phrases best describes hydrophilic? So hydrophilic, and the next question is asking about hydrophobic portion of the phospholipids. Just as a reminder, hydro is referring to water. Phobic, like phobia, means that it is afraid. So hydrophobic is our anti-water portion of the phospholipid. It is nonpolar. It is not interacting with water. No H2O interaction. No, what other words could we be using here? No affinity with water. Or maybe it looks like instead of saying no, it's saying few, as in very little interactions with water. Hydrophilic, which was in question 2, hydrophilic means that it is the lover of water. So philic is referring to loving something. Hydrophilic loves water. It is polar. It interacts with water, touches water, has a high affinity for water. Things like that. So hydrophilic loves the water. Hydrophobic does not love the water, hates the water. That's questions 2 and 3. Question 4 is showing us like a cross diagram of phospholipid bilayer with the heads and the squiggly tails, and it's asking us to drag some descriptions into the boxes to describe the heads and the tails. So we already talked about hydrophobic. This is the part that's afraid of the water, doesn't like the water. In this diagram, the light blue, outside and inside of the cell, that's representing water. So extracellular and intracellular, those are aqueous or water environments interacting with water. So that's going to be something that is hydrophilic. Non-polar, go look on that list that I just made. Non-polar, what does that mean? Hydrophobic, hydrophilic. Phosphate rich. So here you want to look on your notes in section 19.6. The phosphate is the PO4 portion of these phospholipids, the PO4 portion. So is the PO4 portion part of these squiggly tails that are nonpolar, or is the PO4 portion part of the polar heads? When we drew this, the phosphoacylglycerols, you drew the PO4 group pointing either to the left or the right in your notes. And so that should help you figure out if it's part of the head or part of the tail. Select the phrases that describe the plasma membrane. This plasma membrane is just another way of saying cell membrane. So what kind of things does the cell membrane do? Clearly it creates a barrier. Is it rigid, as in stiff, like bony? Let's think about the squiggly, gooey ooiness of phospholipids and all of their little wiggly tails. Do things move through the phospholipids to get in and out of the cell? Creating a barrier between DNA and other intracellular structures. So what that is asking about, do you have the membrane inside of the cell that is blocking the DNA from the interior components of the cell? So here's another cross diagram, and it's asking us some more questions about the lipid bilayer, hydrophobic and hydrophilic. Repelling polar molecules, that would be repelling water. Does that mean it's hydrophobic or hydrophilic? Contains the phosphate, we've already talked about that. The fatty acid chains, those are the tails. The fatty acid chains are the tails. Looks like that box is pointing at the tails. Which of the molecules could align side by side to form a lipid bilayer, side by side? So fatty acids, even though they are part of the cell membrane, they themselves individually do not line up to make the lipid bilayer. You've got to put the fatty acids into the phosphoacylglycerols first. But we did talk about sphingomyelins. That definitely makes a lipid bilayer. Glycerophospholipids, if you look in your notes on 19.6, that's another word for phosphoacylglycerol. So look through the others. Ask yourself, is cholesterol lining up side by side to make the lipid bilayer? What about triacylglycerols? Do they line up side by side? Ooh, facilitated versus active transport. We've got a bunch of things down here that we're going to decide, like moving to the area of low concentration. Is that facilitated or active, or is it both? And all of these should be pretty easy for you to figure out based on your notes. Sodium ion transport, oh, that is in your notes. I'm looking at your notes right now. So you should be good to go with that one. Diffusion versus facilitated transport. So here when they're talking about diffusion, they mean simple diffusion. In your notes, you have simple diffusion. Simple diffusion versus facilitated transport. Some of these might be a little bit tricky. We did talk about glucose, so we know where glucose goes. And moving from an area to low concentration, that's active transport, so that doesn't work here. Protein helps out with facilitated transport, moving across a membrane. Which one requires energy? I don't think either one of them requires energy. Steroid transport into the cell. Now that one is kind of tricky to me, this one, because steroids are big molecules. And so in our notes, we talk about how facilitated transport is used for big molecules, and simple diffusion is used for small molecules. However, steroids are really attracted to the components of cell membranes, and so I feel like steroids might be able to just slip their way into the cell membrane. Think about how steroids like cholesterol can embed itself into the lipoproteins, the HDLs and LDLs. And so I'm going to take a risk on this one, and I'm going to see what it says. No, I have done something wrong. Maybe steroid transport is not either one of these. Let's try again. I clicked it too many times, and so that I just wasted an attempt right there. This is why I'm very forgiving when you ask for forgiveness on Sapling. So maybe steroid transport into the cell is none of these. Oh, I see what I've done wrong. Moving to an area of low concentration. I misread that. Going from high concentration to low concentration. That is true for both of these, not none of these. That must have been painful for you to watch. Let's see if we have it now. No, okay, so I was moving the steroids around because I thought that it was the steroid that was the problem. So I'm going to put steroids back into diffusion, and oh my gosh, I wish that there was a way to just edit that disaster right out of the video. 7 attempts, woohoo! You guys should get this in 1 attempt. And oh my gosh, no, so here is some more. Passive transport versus facilitated transport versus both or neither. So passive transport is another way of saying simple diffusion. And so we've got proteins. We know that that's part of facilitated transport. Going across the membrane is a characteristic of both. Moving to an area of lower concentration, I'm not going to screw that one up again. Neither one of these processes require energy. Bicarbonate is in your notes. Urea is not in your notes. Urea is a small molecule, and I'm actually not sure if it's small enough to qualify for passive transport, but let's give it a try. Oh, look at that. I'm on a roll. Oh my gosh, there's another one. So this time we have facilitated versus active transport. Facilitated diffusion is going to be the same thing as facilitated transport in your notes. Moving to a low concentration, moving across a membrane, requiring energy assisted by proteins. This one should be easy for you to do. I'm going to move on to the next one. Simple versus facilitated diffusion. So simple diffusion versus facilitated transport in our notes. You have carbon dioxide as an example. You have ions listed as being part of facilitated diffusion. You have big molecules like fatty acids and amino acids, which we haven't talked about yet, but they're big molecules. And then we've already done the steroids. Question 13 is asking you to modify the structure to look like cholesterol, which you have in your notes in section 19.8, so you can do that. Question 14 is about HDL and LDL, and you have that in the same section 19.8, so you should have no problem with that. We didn't really talk that much. We didn't really use the word density, but in the name, we wrote out what HDL and LDL stand for. They're both related to density, so that's definitely both of them. We did talk about good versus bad. We talked about the direction of the transportation of cholesterol. So you should be fine with that. Lipids and proteins are in both of them. And so you should be good there. Question 15, more about HDLs and LDLs. And we didn't really talk about the relationship between weight, being overweight, and also exercise, but I am guessing, and increasing consumption of unsaturated fats. but I'm guessing that you can probably rationalize that just by looking at good versus bad. Our nicknames, the good one and the bad one. You can figure those ones out. Here is asking you a question about the ring structure of steroids, which you have in your notes for 19.8. And then these last two, 17 and 18, this is just asking you to don't forget line structures and what they represent. So here you're just going to be counting carbons, counting hydrogens, counting oxygens, and entering in the formula. When you enter the formula in for these molecules, I want you to go carbon first, hydrogen second, oxygen last.